In this second part of this video series on the Briel Replica 1 computer, I'll discuss some of the available hardware add-on boards. If you've not already done so, you should watch part 1 of this series for a general introduction to the Briel Replica 1 computer. The Replica 1 3rd edition and later versions have one Apple I compatible slot. The slot expander board offered by Briel Computers connects to the edge connector and gives you 3 more Apple I expansion slots. It consists of a printed circuit board with some connectors, but does not contain any other components. I can't give a demonstration of the slot expander as I don't own one. It could be useful if you wanted, for example, to use the Apple cassette interface or multi-I/O board and the CFFA1 flash adapter, all of which I'll cover later in this video, at the same time. Note that some of the expansion boards covered in this video will have an addressing conflict and can't be installed at the same time. Also, the first and second versions of the Replica 1 did not have an expansion slot, so the expander was needed in order to provide any expansion capability. Other than that, it's not a highly useful board, as most people likely won't have a need to plug in more than one board, unless perhaps you design something custom yourself that consists of multiple boards. The multi-I/O board is an expansion board for the Replica 1 sold by Briel Computers. It's sold as a kit or assembled and installs in the expansion slot. It has the following on board: a 6551 UART and line drivers for an RS-232 serial port, a 6522 VIA with 2 8-bit I/O ports and timers, a 0 insertion force socket and programmer for 28 C64 EEPROMs, a prototype area, and an optional SpeakJet sound and speech synthesizer chip. Incidentally, the Rockwell 65 series chips used here tended to be a little more powerful than the comparable Motorola serial and PIA chips. One word of warning: for this and any other expansion board, be sure to install it in the proper orientation. Look at the silkscreen pin numbers on the board and the Replica 1. The serial port uses a 6551 chip and can go up to 19,200 bits per second. It provides a standard 9-pin serial connector. A version of the WAS monitor is included that uses the serial port instead of keyboard and screen, so you can upload or download files to a PC. Also supported is an optional SpeakJet chip. This is an IC that can produce speech and sound effects by sending commands to it via a serial port. You cannot use the serial port at the same time as the SpeakJet chip. There's a jumper to select which function to enable. The chip can be easily programmed from BASIC using poke statements. A sample program is included in the Briel manual. I didn't buy a SpeakJet chip with my board, but the chip is available from sources such as SparkFun, and making this video got me thinking that I just might buy one. The cost is about $25. Next up is the 6522 VIA or Versatile Interface Adapter. It provides 2 8-bit bidirectional I/O ports as well as 2 timers and a shift register. The ports can do handshaking and use interrupts. This is useful for any projects that require digital inputs or outputs. The 6522 I/O lines are available on a connector at the edge of the board. Here's a simple example of producing a square wave by toggling one of the outputs. You can see the result on an oscilloscope. The board also has an EEPROM programmer that allows writing to 8 kilobyte 28 C64 chips. You can directly read and write to the chips, although writing cannot be done to consecutive locations at full speed. My JMON monitor program can fill, copy, or move memory with a delay on write to accommodate writing to the slower EEPROMs. Any chip inserted in the 0 insertion force socket shows up at addresses A000 through BFFF. You can use this to program a new EEPROM for the Replica 1. On my board I made one modification. I added a jumper to enable writes to the EEPROM. I put the jumper and pull-up resistor on the prototype area. Note that you can't program PROMs or EEPROMs with this. For that, you need a dedicated PROM programmer, such as this one made by MCU Mall Electronics. If you do this, you might also want to get a low-cost ultraviolet lamp for erasing EEPROMs. You can, however, read from these devices. On my blog and GitHub repository, I posted a series of software experiments demonstrating how to use the hardware on the multi-IO expander board. The Apple Cassette Interface, or ACI, was the only expansion board offered by Apple for the Apple I. It provides mass storage using an external cassette tape drive. This was the most common mass storage format before floppy and hard drives became affordable. This one is from Briel Computers, but is identical to the Apple version, except that it uses a more modern and readily available 27C64 EEPROM, rather than the original 6301 ROMs on the Apple I. The board is installed in an expansion slot. It has two jacks for tape in and out, and an LED which indicates volume level. A whopping 256 bytes of ROM have all of the cassette read and write code. The source code for the ROM has been published, and the original Apple ACI manual is available online and comes on the CD for the Briel ACI. Getting the ACI to work reliably can be tricky. Tape volume is critical, and only certain models of recorders seem to work well. You can use a tape recorder or an iPod or PC sound card. I plan to cover the operation of the ACI in another video. Mike Willigal, who created the Mimeo Apple I replica, also sells an ACI which is identical to the Apple I board, including the ROMs and Apple branding on the PCB. A similar cassette interface was built into the main board of the Apple II. The CFFA1 is a compact flash memory board for the Apple I and Replica I computers. It was designed and made by Richard Dreyer, but can be bought from him or Briel Computers. It provides the ability to load and save files between memory and a file system on a compact flash card. It supports 32 megabytes of storage and stores them in the Apple II ProDOS file system format. This makes it compatible with files stored on a CFFA card which plugs into Apple II computers. It can also expand the memory on a real Apple I to 32K. On a Replica I, much of this memory is already present, so it only expands it by 4K. You can load and save binary as well as Apple I basic programs. It comes as an assembled board which plugs into the expansion slot. You need to provide the compact flash card. This is an older card format. You may have an old card lying around as I did, or you can get an adapter to plug in a newer SD card. Since it only supports 32 megabytes of storage, anything larger than that will not be able to use more than the first 32 meg. 32 megabytes is actually quite a lot, the equivalent of over 200 floppy disks of the Apple II era. The CFFA1 has onboard menu-driven firmware that makes it pretty easy to use. I'll demonstrate that now. First, an example of loading a BASIC program. So to do that, we first go into BASIC and make sure we've done a cold start at least once to initialize BASIC. So here from the WAS monitor, we'll start up BASIC by running from address E000. So we've now initialized BASIC. From BASIC, we can call the address for the CFFA1 menu, which has a very easy to remember address of -24,000. So here we are in the CFFA1 firmware menu. So it's command line driven here. We can see a little help menu of all the different commands, the single letter commands. So for example, we can hit C for catalog and see the files that are on the compact disc. So if we wanted to load a basic game, let's say the horoscope program that I demonstrated in the previous video, we can type L for load and the name of the program. And it then loads it. So from here we can hit Q for quit, and we'll return back into BASIC, which has now loaded the program, so we can run it. And we could start running the program. And I'll see what my horoscope says today. Okay, so now an example of loading a machine language program. In this case, let's run my JMON machine language monitor, which I've previously stored on the SD card. So we'll go back to the CFFA1 menu from BASIC by running call 24000. We can see here the program is called JMON. So we can again hit L for load and the name of the program, the machine language program. It prompts for the start address, and it remembers the address that was stored when the file was saved, which normally is the correct one, so we'll just hit enter. And now to run a machine language program, we can't actually do that from here, so we'll hit reset and go back to the WAS monitor and then start the program up from address 280. And then we then get the prompt for JMON, and we can run the various JMON commands. So for saving a program, it's very similar. You can save basic programs or you can save machine language programs. If we wanted to save a basic program, it's very straightforward. So it actually will go back into the CFFA1 menu, and that actually is something that JMON supports with the M command. So we'll hit M, and to save a basic program, we hit S for save, and it prompts for the name of the program that we want to save. Let's just say foo. And it saves it, and it saves any program that it happens to be in the memory locations used by BASIC. So we now see BASIC program foo show up in a catalog listing. If we want to save a machine language program, we use the W or write command, and it needs a little bit more information. It needs the starting address, let's say 280, the common starting address for programs. The length in bytes in hex, let's say 1000 hex. And the type of program, which normally would be binary, and the name of the program, let's just call it bar. So it's now saved that to memory, and we'd see it in a catalog listing, and we could load it back. So with this card, saving and loading programs is a real breeze. It's 64 megabytes is enough to literally store pretty much every known program that was ever written for the Apple I. In fact, someone's written what he calls the ultimate Apple I software collection. He's collected all the software that he could find for the Apple I and put it on a single CFFA1 disk image that you can download. So really this is a great way to get your hands on a lot of software and quickly load it up and try it. And with one of these boards, it's really hard to go back to using cassette tape with a serial port because this is just so much faster and more convenient. Some time ago, as a little hardware project, I built a memory board on a proto board for the Apple I. It supports two 8K memory chips, which can be either 6264 RAM chips or 28C64 EEPROMs or 2764 EEPROMs. So with it, the Replica 1 is fully loaded with 48K of contiguous RAM. It's got jumpers which enable writing for each chip, so you can write protect the memory if desired. It uses a vector wire wrap proto board which has the right edge connector for the Apple I expansion slot. A parts list and schematic can be found on my GitHub account. In part 1 of this video series, I mentioned I have a 65C02 currently installed in my Replica 1. I'll say a little more about it. The 65C02 microprocessor is an upgraded CMOS version of the MOS Technology 6502 8-bit CPU. Over the years, it's been manufactured by Western Design Center, NCR, GTE, Rockwell, Synertech, and Sanyo. It's electrically compatible with the 6502 and offers lower power consumption due to the use of CMOS technology. Probably the most interesting feature is that it supports some new instructions. Briefly, the new features are a new zero-page addressing mode for 8 of the commonly used instructions, new accumulator decrement and increment instructions, a new jump instruction with absolute indirect addressing mode, a branch always instruction, instructions to push and pull the X and Y registers from the stack, a new store 0 instruction, and test and reset and test and set bit instructions. 4 additional instructions are available on the 65C02s manufactured by Rockwell and WDC. A branch on bit reset or set and reset or set memory bit instructions. Two additional instructions are available on the 65C02s manufactured by WDC or Western Design Center: a stop the processor instruction and a wait for interrupt instruction. Any unused op codes are handled as no ops by the 65C02, where with the 6502 the behavior was undocumented. If you bought the Replica 1, your kit may have actually come with a 65C02. If not, you can order one and just simply replace it with the 6502 with a 65C02. While no longer manufactured, it's available as new old stock from suppliers such as Jameco. And I ordered one, received a Rockwell R65C02P2, which can run up to 2 MHz and has a date code from 2003. The 65C02 will continue to run all existing 6502 code, but you can also experiment with the new 65C02 instructions, and your CPU will consume less power and run cooler. The version of the Crusader assembler burned into ROM in the Replica 1 doesn't support the 65C02, but there is a 65C02 version of Crusader available. You can download that version and program it into an EEPROM if you have the facility to do so, or you can run it from RAM. On screen here is my JMON program using its disassembler mode that supports 65C02 instructions. Some computers, such as the Apple IIc, shipped with a 65C02. The Apple IIgs, the last of the Apple II series, used a 16-bit version of the 6502 processor called the 65C816. The Western Design Center 65816 is backwards software compatible with the 6502 and 65C02, but not electrically compatible. There was a chip, the 65802, which was electrically compatible with the 6502, but it's no longer manufactured. The 65816 is still available, and I was intrigued to find a couple of designs on the internet for an adapter board which made it compatible with the 6502. I decided to try building an adapter board for the 65816. I built mine on a proto board and used two 40-pin dip headers and a short piece of ribbon cable to attach it to the Replica 1 CPU socket. The 65816 comes up in emulation mode where it's software compatible with the 6502 and 65C02. It also implements a number of new instructions, some of which are in the 65C02 and some are new ones. You can switch the 65816 to native mode at any time under software control. Native mode offers 16-bit X and Y registers and accumulator, a 24-bit address space, allowing you to address 16 megabytes, new instructions, and new addressing modes. In native mode, you can independently configure whether the accumulator and index registers are 8 or 16 bits. Zero page, now called direct page, and the stack can be relocated anywhere in memory. The chip is not electrically compatible with the 6502 or 65C02, but it's not much different. The adapter I constructed makes it compatible, or at least compatible enough for the Replica 1. There are some limitations of the adapter. The system still only has 16 address lines, so 16 megabytes of addressing is not possible. The extra 8 high-order address lines are ignored. Some hardware pins are also not supported, such as set overflow and sync, but these are not used on the Replica 1. Having 16-bit registers is a nice luxury, and you can still use 8 bits when you need it by switching modes, which can save speed and code size. There are even two new memory copy instructions which can copy a range of memory up to the full address space in a single instruction. On my GitHub account are some demo programs that demonstrate some of the 65816 instructions. They compile with the CA65 assembler, which fully supports the 65816 instruction set. It even has a smart mode where the assembler tracks whether the CPU is in 8 or 16-bit accumulator and index register modes and generates the code accordingly. My JMON monitor program, which I plan to cover in a future video, can also disassemble 65816 code. This video covered some of the Apple I and Replica 1 hardware add-on boards that I'm familiar with. There are some other add-on boards which have been designed. Wendell Sander, who is perhaps best known as the designer of the Apple III, has designed some boards which he has put in the public domain. In a future video, I may describe some of the more interesting software and software tools available for the Replica 1.